Okay, welcome back to the trigonometry lectures on educator.com, and today we're talking about the identity Tansquaredx plus 1 equals secant squared x. And you really want to think about this as a kind of companion identity to the main Pythagorean identity, which is that sine squared x plus cosine squared x equals 1. So hopefully you've really memorized this identity, sine squared x plus cosine squared x equals 1. That's one that comes up everywhere in trigonometry. And then sort of the companion Pythagorean identity to that for secants and tangents is tan squared x plus 1 equals secant squared x. And there's another related identity, essentially just the same thing for cotangents and cosequents, is that cotangent squared x plus 1 equals cosecant squared x. And you may wonder how you remember these identities. For example, how do you remember whether it's tan squared plus 1 equals secant squared, or maybe it's the other way around. Maybe it's secant squared plus 1 equals tangent squared. Well, really the answer to that lies in the exercises that we're about to do. We'll show you how to derive those identities from the original one, sine squared plus cosine squared equals 1. So as long as you can remember sine squared plus cosine squared equals 1, we'll learn how you can use that to figure out the others, and you really won't have to work very hard to remember these new Pythagorean identities. So let's jump right into that. The first example here is to prove the identity tan squared x plus 1 equals secant squared x. So the trick there is to remember the original Pythagorean identity, which is cosine squared x plus sine squared x is equal to 1. That's the original Pythagorean identity. And that's one that you really should memorize and remember throughout all your work with trigonometry. And then what you do to manipulate this into the new identity is you just divide both sides by cosine squared x. And so on the left we get cosine squared x over cosine squared x plus, let me write it as sine x over cosine x squared equals 1 over cosine x squared. And then of course cosine squared over cosine squared is just 1. Sine over cosine, remember that's the definition of tangent. So this is tangent squared x. 1 over cosine, that's the definition of secant x. So secant squared x. And so you can just rearrange this into tangent squared x plus 1 equals secant squared x. And so that shows that this new identity is just a straight consequence of the original Pythagorean identity. So really, if you can remember that original Pythagorean identity, you can pretty quickly work out this new Pythagorean identity for tangents and cotangents. Let's try using the Pythagorean identity for tangents and cotangents. In this problem, we're given that tangent theta is negative 4.21, and theta is between pi over 2 and pi, and we want to find secant theta. So, remembering the Pythagorean identity, tan squared theta plus 1 is equal to secant squared theta. And so if we plug in what we're given here, tangent squared theta, that's negative 4.21 squared plus 1 is equal to secant squared theta. Well, 4.21 squared, that's something I'm going to work out on my calculator. Is 17.7241. So 17.7241 plus 1 is secant squared theta. So that's 18.7241 is secant squared theta. And so if I take the square root of both sides, I get secant theta is equal to plus or minus the square root of 18.7241. And again, I'm going to do that square root on the calculator. And I get approximately 4.33. The question here is whether we want the positive or negative square root. And that's where we use the other piece of information that was given in the problem. Theta is in the second quadrant here. Theta is between pi over 2 and pi. So theta is somewhere over here. Now secant theta, remember, is 1 over cosine theta. In the second quadrant, if you remember, all students take calculus. In the second quadrant, sine is positive, but cosine is not. So cosine is negative, and that means that secant theta is negative. Theta is in quadrant 2. So cosine of theta is negative. So secant theta, because that's 1 over cosine theta, is negative. So secant theta, we want to take the negative square root there, and we get an approximate value of negative 4.33. So that negative is very important. So the key to that problem is, first of all, invoking this Pythagorean identity. Tangent squared plus 1 is equal to secant squared. So that's very important to remember. We plug in the value that we're given, and then we work it through and we try to solve for secant theta, but we get this plus or minus at the end because we don't know if we want the positive square root or the negative square root. That's where we use the fact that theta is in the second quadrant. Since theta is in the second quadrant, cosine theta must be negative, and so secant theta, remember, is just 1 over cosine theta, must also be negative. That's how we know we want the negative square root there, so we get negative 4.33. In our next example, we're given a trigonometric identity and we're asked to prove it. Cosecant theta minus cotangent theta over secant theta minus 1 is equal to cotangent theta. So I'm going to start with the left-hand side of this trigonometric identity, and I'm going to manipulate it. I'm going to try to manipulate it into the right-hand side. So the left-hand side, which is cosecant theta minus cotangent theta over secant theta minus 1. Now I'm going to do something clever here, and it's based on this old principle of whenever you have an a minus b in the denominator, try multiplying by the conjugate, a plus b over a plus b. Or if it's the other way around, if you have a plus b, you multiply by the conjugate a minus b over a minus b. The reason you do that is that it makes the denominator a squared minus b squared. We're taking advantage of that old formula from algebra, the difference of squares formula. And a lot of times the a squared minus b squared formula is something that'll simplify into something nice. That's what's going to happen here. We're going to multiply, since we have secant theta minus 1 in the denominator, by secant theta plus 1. Secant theta plus 1. And so what that turns into in the denominator is this a squared minus b squared form. So secant squared theta minus 1. The numerator really doesn't have anything very good happening yet. Cosecant theta minus cotangent theta. Quantity times secant theta plus 1. So nothing very good happening in the numerator yet. But in the denominator, we're going to take advantage of the fact that tangent squared theta plus 1 is equal to secant squared theta. That's the Pythagorean identity that we're studying today. If you move that around, you get secant squared theta minus 1 is equal to tangent squared theta. So that converts the denominator into tangent squared theta. So that's very useful. In the numerator, we have cosecant theta minus cotangent theta and secant theta plus 1. I think now I'm going to translate everything into sines and cosines because those will be easier to understand than cosecants and cotangents. So cosecant, remember, is 1 over sine theta minus cotangent is cosine theta over sine theta. Secant theta plus 1, well, secant theta is 1 over cosine theta. And tangent theta, if we translate that into sines over cosines, that's sine squared theta over cosine squared theta. So now I've got fractions divided by fractions. I think the easiest thing to do here is to bring the denominator, flip it up and multiply it by the numerator. So we'll get cosine squared theta over sine squared theta. That's flipping up the denominator. And then the old numerator is, if I combine the first two terms of the first one, it's 1 minus cosine theta over sine theta. And in the second one, we have 1 over cosine theta plus 1. Now, I think what I'm going to do is I'm going to look at this cosine squared, write it as cosine theta times cosine theta, and then pull one of those cosines over and multiply it by this term and try to simplify things a little bit that way. So that'll leave me with just one cosine left. Still have sine squared in the denominator. 1 minus cosine theta over sine theta times, now cosine theta times 1 over cosine theta is 1 plus 1 times cosine theta. And now look, we have 1 minus cosine theta times 1 plus cosine theta. So we're going to use this pattern again. The a minus b times a plus b is a squared minus b squared. So I have cosine theta over sine theta, or sine squared theta. Now, multiplying 1 minus cosine times 1 plus cosine gives us 1 minus cosine squared theta and sine theta in the denominator. Well, now we're going to use the other Pythagorean identity, the original one, which I'll write over here. Sine squared theta plus cosine squared theta equals 1. And so if you switch that around, 1 minus cosine squared theta is sine squared theta. So I plug that in, cosine theta over sine theta. 1 minus cosine squared theta now translates into sine squared theta, all divided by sine theta. And I forgot my little squared there. That's from the line above. And now we have some cancellation. Sine squared thetas cancel. We get cosine theta over sine theta. But that's cotangent theta. By definition of cotangent, cotangent is defined to be cosine over sine. And that's exactly equal to the right-hand side of the identity. So when you're proving these trigonometric identities, you pick one side and you manipulate it as much as you can. You try to manipulate it into the other side. And it does take some trial and error. I worked this problem out ahead of time. I tried a couple different things, and I finally found a way that gets us through it relatively quickly. So it's not like you'll always know exactly which path to follow. It takes a little bit of experimentation. But there are some patterns that you see over and over again. And the two patterns that we really invoked strongly in this one are this algebra pattern where a minus b times a plus b is equal to a squared minus b squared. So essentially, whenever you see an a minus b or an a plus b, think about multiplying it by the conjugate and then taking advantage of that pattern. So that's what really got us started on the first step here. We had a secant theta minus 1, and I thought, okay, let's multiply that by secant theta plus 1. That gives us secant squared theta minus 1. The second pattern that we used there was to invoke these Pythagorean identities. Tan squared plus 1 equals secant squared, and sine squared plus cosine squared equals 1. So we invoked that one here, converting secant squared minus 1 into tan squared. And then later on, when we had another a minus b times a plus b, it converted into 1 minus cosine squared, and that in turn, by the Pythagorean identity, converted into sine squared. So it's just a lot of manipulation, but you can let your manipulation be kind of guided by these common algebraic identities and these common Pythagorean identities. And then you just try to keep manipulating until you get to the other side of the equation. So we'll try some more examples later on.